Now we're going to talk about the selectivity of radical halogenation reactions. Again, radical halogenation reactions will add a halogen in place of a hydrogen atom. Before we talked about chlorination, but you can also use bromination. In a chlorination reaction, you should recall that the secondary product is favored, but you will also get a mixture of the primary alkyl chloride. If we switch the halogen from chlorine to bromine, this reaction becomes much more selective. In fact, when we use bromine, we have 97% of the secondary product and only 3% of the primary product. This is much more synthetically useful because we don't have a mixture of products. To understand why this occurs, we have to recognize that radical chlorination and radical bromination reactions are energetically different. Let's figure out how. Well, let's take a look at the propagation step, the first propagation step of a chlorination. We have a chlorine radical, which can abstract a proton from our propane, generating a secondary radical as well as HCl. Let's plot all of these on a reaction coordinate diagram. First, the starting material is a relatively high energy. We've got this chlorine radical and we have propane. The products in this case are actually a little bit lower in energy because an HCl bond is relatively strong. We also have a secondary radical which is stabilized because it's secondary. Because this reaction is exothermic, the transition state is going to look more like the starting material than the product. So it'll look a little bit more like the propane than a radical. And then the reaction relaxes back down as it proceeds. Let's take a look at the case with a radical bromination. Bromine is going to be a more stable radical than chlorine. This is important because bromine is larger. It has a larger polarizability, so it doesn't notice the loss of that one extra electron as much as chlorine does because chlorine is smaller. Let's think about the energy of the products here. HBr is actually higher in energy than HCl. The bond isn't as strong. In terms of acidity, HBr is a stronger acid than HCl. And again, because if we generate a bromide ion, it's going to be more stable because it's larger than if we generate a chloride ion, which is smaller. If we add in the energy of our transition state here, you should notice that it takes a long time, it takes a lot of activation energy to get to this point, because this reaction is actually endothermic. And then we have a relaxation back down to our product. In the case of an endothermic reaction, the transition state is going to more closely resemble the product. So in this case, it looks more like a radical. Because it looks more like a radical, you're going to form the more favored radical, the more stable radical. The activation energy for a primary radical in this case would be much higher. It would be somewhere around here. If we apply this to fluorine, fluorine would be even more exothermic than chlorine would, so a radical fluorination really can't be used because it's completely non-selective. In fact, you'll get multiple fluorination reactions. In the case of iodine, instead of bromine, iodine is even more endothermic, so it takes so much activation energy that the reaction is just too sluggish to be useful. So in this case, we would have to stick with either chlorine or bromine for our halogenation reactions. So to summarize, radical chlorinations are non-selective. They're going to form primary, secondary, and tertiary products because the transition state is more similar to the starting material, which does not have a radical character. Radical brominations, however, are more selective. They will form predominantly the most substituted products because forming the radicals in endothermic reaction, the transition state will more closely resemble the radical, and a secondary or tertiary radical will always be more stable, so that will be formed preferentially.